So I'm looking down on two train tracks. They're side by side, parallel to each other. And let's suppose on that top train track there's a blue train, and you're in the blue train. You're driving the blue train. You're in the locomotive, and you're looking at the speedometer, and it says that your speed is a cool 50 miles per hour. And in fact, let's make that a velocity. It's 50 miles per hour in the i-hat direction. That means to the right. And furthermore, let's suppose there's this other train right beside you cruising in the same direction, and it's going faster than you. But you can't see inside the locomotive. You can't see its speedometer. You can just tell it's going faster than you, but you want to know how fast it's going. You want to know its velocity. So is there any way for you to determine the velocity of the red train? So here's what you're going to do. You're going to be smart. You're going to take out your stopwatch, and you're going to observe things over a period of 30 seconds. In particular, over this period of 30 seconds, you're going to observe that 10 boxcars pass you by. That is 10 boxcars on this red train. They fly past you. And then, being a clever engineer that you are, you're going to notice that the distance between the beginning of one boxcar and the beginning of the next boxcar, let's say that's 70 feet. I don't know exactly what that is, but let's just suppose for the argument we got 70 feet. So we're going to take this 10 boxcars per 30 seconds and we're going to multiply it by 70 feet per boxcar. So now in my mathematical relationship, you'll notice that my boxcars cancel out, and what I have left is 10 times 70, or let's say 700 feet per 30 seconds. So I got 700 feet of red train going past you in that 30 seconds. And if you work out the math, this is 23 1/3 feet for every second going past you. That's how much faster the red train's going, right? So now if I take this 23 1/3 feet for every second, and then I observe that, what? I've got 5,280 feet in 1 mile, and I have 3,600 seconds in 1 hour. And what does that do for me? Notice that my feet over up top cancels out my feet down below, and I've got a second down in the denominator, and I have a second up here in the numerator. So if I combine all that good stuff, what do I get? I get 15.91. I have miles on the top per hour on the bottom. 15.91 miles per hour. So let's think about what this 15.91 miles per hour means. That means, remember, we're sitting on the blue train watching the red train go by. From the vantage point of the blue train, it looks as though the red train is moving at a rate of 15.91 miles per hour to the right. Now we have some terminology for just this case. We say that that 15.91 miles per hour, that's the velocity of the red train relative to the blue train. Again, we're sitting on the blue train watching the red train. It looks as though it's going 15.91 miles per hour to the right. Now let me go back to my original question. What was the velocity of the red train? Well, I hope you can think about what this means. We know that the velocity of the blue train was 50 miles per hour. The velocity of the red train was 15.91 miles per hour faster. So to get the velocity of the red train, I would just simply take the velocity of the blue train and add in the velocity of the red train relative to the blue train, right? So that should give me, 65.91 miles per hour to the right. Make sense? Now you may not have thought very much of it, but what we just did is we thought through one of the very important concepts that we're going to be using for the rest of the semester. That is this concept of relative velocity. We say the velocity of one object, in this case the red object, equals the velocity of the blue object plus the velocity of the red object relative to the blue object. This is a notion of relative velocity, and I think you'll agree that it makes sense, right? Okay, let's take a more general case where I have a red particle and a blue particle and they're moving around in this two-dimensional plane. I can make this a three-dimensional space instead of a two-dimensional space, but since two-dimensional spaces are easier to draw, that's what I'm going to stick with. The story for 3 dimensions is exactly the same. So what I'm going to do is suppose the red particle is moving along some path like this, and the blue particle is moving along some other path like that. But at this one instant, I'm taking a snapshot and I'm getting their positions. At this first instance, we'll let this vector right here denote the position of the red particle. I'll call that RR, position of the red particle. And furthermore, we can write the position of the blue particle as RB. Now the next thing I'm going to do is define another vector that's this one right here. What is this? It's a vector that starts at the blue particle and goes to the red particle, and I call this one R, position of the red particle relative to the blue particle. And it's exactly what we had with the trains, right? We're sitting on the blue particle and we're looking at the red particle, just like we're sitting on the blue train looking at the red train go by. In this case, we're just looking at the position. So the position of the red particle, as if we're just sitting on the blue particle, that's my position of red relative to blue. Now I can do a little bit of vector addition here. Notice that the position of the red particle, what is that? I can write that as the sum of these two vectors. That is, I can write it as the sum of the blue position of the blue particle, that vector right there, plus this one right here, plus position of red relative to blue. Ooh, interesting, huh? So position of red equals position of blue plus that relative position, red relative to blue. Now before we go on with this, I want to make one little observation. That is, I can rearrange the terms in here. I can take the RB and move it over to the other side. In other words, I can say R, position of R minus the position of B. Brought that over to the other side. So this is equal to R, position of R relative to B. So here's another definition of position of red relative to blue. I just take the difference between the position of red minus the position of blue. Okay, so that's a little aside, that little formula that you might find handy dandy. Alright, so let's go back to this position equation that I have. And what I'm going to do is I'm going to take a time derivative of each term. Take the time derivative of each term in an equation. I still have an equality here, right? The stuff on the left is equal to the stuff on the right. But notice what's the stuff on the left. I'm taking a time derivative of the position R. Well, by definition, that's the velocity of the red particle, isn't it? Aha! Time derivative of the position B, well, that's the velocity of the blue particle. And then what we have left here is a time derivative of red relative to blue. I call this the relative velocity of red relative to velocity of blue. And do you see something here that we've seen before? This is the exact same expression we had for the trains, for the relative velocities, right? We just derived it for a more general circumstance. So this is a very important principle. And I noticed that I had a little typo already. So what goes in the last piece is the velocity of red relative to blue. What that means, remember, velocity of red relative to blue. That means we're sitting on blue and we're watching red and seeing what its velocity is, right? And the relationship between velocities is given by this expression right here. Really nice. All right, so we're going to do this exactly one more time. We're going to take a second time derivative. So 2 dots over each one of these positions, and then we have the second time derivative of the red position. Of course, that's an acceleration of the red particle, and this has to equal the second time derivative of the blue particle, or the acceleration of the blue particle. And then the second time derivative of this relative position, that's what we're going to call the acceleration of red relative to blue. And again, this is another one of these fundamental kinematic relationships that we're going to use. That is, the acceleration of the red particle is equal to the acceleration of the blue particle plus the acceleration of red relative to blue. It's kind of like the thing we had with the trains, but now the velocities are changing in time. But nonetheless, here's my expression. Remember, the acceleration of red relative to blue. What does that mean? It means we're sitting on blue, observing what red is doing. As we're standing on blue, looking at red, that's that relative acceleration we measure. All right, so there's your expressions for relative position. Oops, we had position before I started taking derivatives. Relative velocity and relative acceleration.